Okay, lesson for today is lesson 16, and the title is Graphs Can Solve Equations Too. So first we're going to look at the opening exercise and how we solve it algebraically, and then how in exercise 2 how we can actually solve the equation by just looking at the graph and not having to solve it using algebra. Okay, so let's look at the first exercise. It says solve for x in the following equation. So we have absolute value of x plus 2 minus 3 equals 0.5 x plus 1. So the way we solve this is first by isolating the absolute value expression and separating the solution into two cases. So first I isolate the absolute value, so I add 3 on both sides. So I have the absolute value of x plus 2 equal to 0.5x plus 4, okay, 1 plus 3. So the two cases that I was talking about, the case 1 would be when the absolute value expression is represented by the distance from 0 into the positive direction. Okay, so when we do that into the positive direction, we have x plus 2 equals 0.5x plus 4. Okay, so and then case 2 will be x plus 2 equals to 0.5x plus 4, but we make that into a negative, so that's when it goes into the negative direction. So once we get our two cases, we can solve for x. So in case 1, that is represented by the distance from 0 into the positive direction. This is positive direction, and this will be the negative direction. In the positive direction, I want to isolate the x. Okay, so I subtract 0.5 on both sides, and I end up with 0.5x, and then I subtracted 2 on both sides, and I end up with 2 on the right. Okay, so x equals 4. So basically I just solved for x from that equation. In this case, it's a bit more complicated because we have the negative. So we have x plus 2 stayed the same, equals negative 0.5x minus 4. So now I subtract 2 on both sides and also add 0.5x on both sides. I'm trying to do it simultaneously because now we know how to solve these, and x or 1x plus 0.5x gives us 1.5x. Okay, these two cancel, and these two cancel, and I end up with negative 4 minus 2, which is negative 6. So now when I divide 1.5 into negative 6, x is negative 4. So these are my two solutions for the opening exercise, 4 and negative 4. Let's look at exercise 2. So now it says let f of x be absolute value of x plus 2 minus 3, so the same as before, and g of x be the other function, which is 0.5x plus 1. So the goal is to graph these two functions where y equals f of x and y equals g of x. And we're going to solve for x using just visually the graph of the functions. Okay, so we don't have to do all this work that we did in exercise 1. So let's graph these two functions. So you can use the calculators that we have available, TI-83s, or right now I'm using Desmos on my phone. Okay, so the first equation is f of x equals the absolute value of x plus 2, so x plus 2 minus 3. Okay, so that's the first function, and then I press enter and I plug in the other function, which is 0.5x plus 1. So now I have the other function. So the first one is in green, the other one is in, or I'm sorry, the first one is in blue, the piecewise function, right? Because we have the absolute value, and the second one is in green, just the equation of the line. It's a linear equation. So now that we found this, we can put that on our graph on the paper. Okay, so I just drew them on the graph as well. So the question B says, when does f of x equals g of x? So what is the at the intersection point? Okay, what is the visual significance of the points where f of x equals g of x? So the f of x will equal the g of x when x is 4, and also when x is negative 4. Okay, x is 4, x is negative 4, and the points are in this case 4 and 3, 4 and 3, and the other point was negative 4 and negative 1. So the points where f of x equals g are the intersection. So the meaning, the significance, is that that's where the graphs intersect. So I just wrote down the points where f function of x equals the function of g are the intersection of the graph f and the graph g. Okay, so you can clearly see that these are the 2 points where the 2 lines or the 2 graphs meet. Okay, so now let's look at question C. Is each intersection point x and y an element of the graph f and an element of the graph g? In other words, do the function f and g really have the same value when x is 4? What about when x is negative 4? So the answer is simple yes. Yeah, you can determine this if we plug in negative 4 and 4 for x in both of the function. So you can have so let's say we're going to use the point negative 4 and negative 1. Okay, you know that this is x and this is y, or f of x. Okay, so we're going to use our f of x. So we're going to use that, negative 1, to make it equal to the absolute value of x plus 2. So in this case, we're going to replace the x with negative 4. So absolute value of negative 4 plus 2 minus 3. Okay, we're going to use this function, the f of x. So in this case, we're going to have negative 1 equals absolute value of 2, right? Because negative 4 plus 2 is negative 2. Absolute value of negative 2 is going to be 2 minus 3. So negative 1 equals negative 1. So it does check. And also in the other one, so then I plug in the value for x, negative 4. I plug in for x in this case. So you end up with negative 1 equals 0.5 times negative 4 is negative 2. Negative 2 minus 1 is negative 1. So it does check again that that negative 4 is a solution for our equation. Now we need to find out if it checks for 4, right? Because we had 2 points. We had this one, x equals 4, and then x equals negative 4. So right now we just checked for x equals negative 4. So now we're going to use the other point, positive 4 and 3. So when x is 4, and then f of x or g of x are 3. So in the first case, for f of g, I use 3, right, for f of g, equals to the absolute value of, instead of using the x here, I'm using 4 plus 2 and then minus 3. So I end up with 3 equals 4 plus 2 is 6 minus 3. 3 equals 3. So it checks again. And the last one, g of x. So we're going to have 3 for g of x, right? This 3 equals to 0.5 times x, but in this case x is 4, so I plug in 4 for x. Remember, we're using this formula up here, the g of x formula, which is 0.5 times x plus 1. And plus 1 down here. So I end up with 3 equals 0.5 times 4 is 2 plus 1 equals 3. So 3 equals 3, and it checks again. I know checking to verify it's a tedious process, but we don't have to do that every time. Okay, as long as we know how to graph it, we should be okay. All right, so let's look at example 1 on page 104. Solve this equation by graphing the two functions on the same Cartesian plane. So you have this function right here, and then this function right here. So you have two different functions, so let f of x be the first function, so this function be f of x, and the other function be g of x. Okay, so now using the calculators, let's plug those in. I'll plug it into my Desmos and see what we can come up with. So once I plug my equations into Desmos.com, I came up with something like this. Okay, they're both piecewise functions, and we have to just kind of zoom in on this graph to see where they intersect. And it looks like the first intersection point is at x is at negative 4, okay, and the y is at 1, 2, 3, 3. Okay, so negative, looks like it's a negative 4 and 3. Okay, you can actually make it bigger so you can see the whole thing. Okay, oh, I'm sorry, negative 3. So it's at negative 4 and negative 3. And the second point where they intersect, if you scroll to the other side, you actually see that it's at when x is 8 and y is negative 2. So now we have a little fill in the blanks. From the graph, we see the two intersection points are negative 4 and negative 3, and 8 and negative 1. So when you scroll down, it says the fact that the graphs of the functions meet at these 2 points, it means that when x is negative 4, then both of those f of x and g of x are negative 3. And then when x is 8, then both of those are negative 1. So both of these expressions, negative absolute value of x minus 3 plus 4 and absolute value of 0.5 x minus 5 are equal when x is negative 4 and then when x is 8. okay, and this is the